Okay, so today we're going to be going over section 9.4 and we're going to be talking about comparisons of series. As I mentioned before last time, what we're going to be doing in these next couple sections is trying to determine whether a series converges or diverges. We're not going to necessarily be able to tell what it converges to, but we just want to know if it converges or diverges. To be able to do that, we're going to compare our series in this section, we're going to be talking about comparison tests, and we need to have something to compare it to. And so two of the series that we've come across that we know very well what they do is the geometric series. So a constant times a common ratio raised to the input power. That's what the geometric series looks like. And this series will converge whenever the absolute value of your common ratio is less than 1. And if the absolute value of your common ratio is bigger than 1, then the series diverges. In the case of a geometric series, we also know what it converges to. We have a formula for that. The series will always converge to the first term divided by 1 minus the common ratio. The next series that we have, and we only have two, is a p-series. So this is what the p-series looks like. 1 over your input to a constant power. So 1 over k to the p. And we saw in the last section using the integral test that this series is going to converge whenever p is bigger than 1, and it's going to diverge for values of p between 0 and 1, including 1. And so we're going to be comparing series, and we're primarily going to be comparing them to these two because these we know what they do just by looking at them. Before we get to that, I'd like to go over a calculation with you that we did last semester. We were trying to find the limit as n goes off to infinity of something like n squared, 3n squared plus 4n minus 8. And in the denominator we would have 4n squared minus 6n plus 5. And the trick that we did is we multiplied the numerator and the denominator by 1 over the largest power in the denominator. And so we multiplied by 1 over n squared. And it was always 1 over the largest power in the denominator. And so then this becomes the limit as n goes off to infinity of, and so then you'd get 3 plus 4 over n minus 8 over n squared. And in the denominator 4 minus 6 over n plus 5 over n squared, right? And again, what's going on here is that everything with a variable in the denominator, because the variable is going off to positive infinity, would go to 0. And so then your limit would just be whatever's left, the 3 over the 4. And so your limit would be 3/4. But notice that when you rewrite the expression in this form right here, what you are saying is that for very large values of x, your expression 3n squared plus 4n minus 8, all divided by 4n squared minus 6n plus 5, is approximately the same thing as the 3n squared over the 4n squared. And that is exactly equal to 3/4 because the n squareds will go away. And so there's some results there that you can use from throughout the class. But what we're really going to use today is that when you have a fraction of two expressions, you can forget pretty much all but the fastest growing terms, right? So we have 3 terms here, and we can pretty much forget about the 4n and the minus 8 in the numerator and the minus 6n and plus 5 in the denominator, and just look at the 3n squared over the 4n squared, which gives us this 3/4. That's because all of these other terms get closer and closer to 0 as n gets bigger and bigger. So that's what for large values of n, when you have fractions, you can ignore all but the fastest growing terms, and you just have a single term in the numerator and the single term in the denominator. That's going to be important for what we're going to do today. So going back to our work, We now want to go over this result that's going to make things a little easier for you. Result, for any two positive numbers, if A is bigger than B, then 1 over A has to be less than 1 over B. And so again, what this says is the inequality on the right says that if you have one pizza shared with A people, and you have A is bigger than B, then the slice that each one gets is going to be less than the slice that each one gets over here, because over here you have less people, because A is bigger than B. It's pretty much the same thing over here. If A is less than B, then 1 over A has to be bigger than 1 over B. You have less people over here, so when you find the reciprocal of each one, the slices are bigger, right? And so that's what this 1 over A is, the slice that each person gets. So what this tells you is that when you, if you're working with positive numbers, if you have an inequality, when you flip it, you reverse the inequality symbol. That's the practical view of that, what we're going to use it for. So you should be able to answer this question. So you should take a moment, pause the video, and convince yourself of whether this series converges or diverges, or why. Now again, all you know right now is what geometric series do and what p-series do. So at this point, you should be able to recognize this as a geometric series or as a p-series. So let's get back to our problem. Does the series converge or diverge? Why? Now, this doesn't look like a geometric series the way it is written, but if you rewrite it using your algebra skills, this is 1 over 3 to the n, variables in the exponent, your base is constant, 1/3, and so then this is 1/3 plus 1/9 plus 1 over 27, and so on. And your common ratio is 1/3, and so then this is a geometric series, and it converges because our common ratio is between -1 and 1. So all the question asks is, does the series converge or diverge? Yes, in this case, we actually know what it converges to. It will converge to the first term, 1/3, over 1 minus the common ratio, 1/3, which is then 1/3 divided by 2/3, which is then, if we multiply the numerator and denominator by 3, 1/2. Now, take a moment and look at the next series. And this is a new type of series. This is not a geometric series. You should ask yourself, why is this not a geometric series? How is this different than the last series? You should see that plus 4 makes this not a geometric series. But what does that plus 4 do to the terms of the series? Does it make them smaller? Does it make them bigger? And then since you know what 1 over 3 to the n does, we just decided in the last slide that converged, what should this do? Okay, so again, we're looking at this asking, well, what should this do? It should be very clear to you that 3 to the n plus 4 is bigger than just 3 to the n. So when I flip both sides, when I get 1 over 3 to the n plus 4, that should reverse the inequality, and that should be less than 1 over 3 to the n. Now, we know that if I add up all these terms from the last slide, those will converge, and these are even smaller. So it should make sense that this series converges. What does it converge to? We don't know. We can't figure that out yet. But we should know that because the terms are smaller than those of a converging series, these terms should converge. Now, let's look at the next slide. On the next slide, we have this series. Take a moment to decide what you think this series should do. The summation from k equals 1 to infinity of 1 over 2 times the square root of k. And again, we only have two series that you should know. You should know the p-series and you should know the geometric series. So decide what this does. Okay, so Obviously, this is not a geometric series. We don't have a common base raised to a power. The base is changing. We have the square root of x. I'm sorry, the square root of k here. But we can rewrite this as, now be careful with this 2 here. You might think that that 2 matters, but because it's a constant, from our limit laws, we can take out that 1/2. And then we have the summation of 1 over, and instead of writing the square root of k, we can write it as an exponent, k to the 1/2. Now, when you see it like this, then you see that this is a p-series, with your p being 1/2, and because 1/2 is less than 1, and this diverges. So you need to be there, where you can just look at a series like this and decide what it does. And let's look at our next slide. Let's look at this series. Very similar to the last series that we just saw. We have 1 over 2 times the square root of k minus 1. We've added this extra minus 1 to it. You should pause the video and ask yourself, what does that minus 1 do to the terms? Does it make them bigger? Does it make them smaller? And so since it changes the terms in that manner, so then what does that do to the series? Will my series converge? Will my series diverge? And take a moment, pause it, try and answer that question. Okay, hopefully you've taken some time to think about this. Now, obviously, 2 times the square root of k minus 1 is less than 2 times the square root of k. You've subtracted 1 from it, so you're going to get a smaller number. And so then when I flip it, 1 over 2 times the square root of k minus 1 is going to be bigger than 1 over 2 times the square root of k. We had already decided that 1 over 2 times the square root of k diverged because it's a p-series, with p being equal to 1/2. And the terms of this series are even bigger, right? So then this sum will be bigger than the sum of the other one, but the other one diverged, so then this thing has to diverge. And diverges because it's bigger than the terms of the diverging p-series. So that should make sense. And so that brings us to our theorem. It should be fairly intuitive. It's called the direct comparison test. We're directly comparing 2 series. We've seen this in the last 2 examples. It should make sense. And it just says this test is only going to be for positive terms to keep things simple. That if an is less than bn, if you know that the bigger one converges, then the smaller one has to converge as well. That's what we saw in our 2 examples, in our first example. Now, if the smaller one diverges, then the bigger one has to also diverge, right? Now, you have to be careful with this, right? You have to compare your series to an appropriate series, and we'll get comfortable with that in the exercises. We have a remark here. As stated, the direct comparison test requires that a sub n is less than or equal to b sub n for all n. Because the convergence of a series is not dependent on its first several terms, you could modify the test to require only that a sub n be less than or equal to b sub n for all n greater than some integer n. So maybe it doesn't happen for the first 4 or 5 terms. Maybe it happens after that. So as long as it's eventually the case that a sub n is less than or equal to b sub n, then your test applies. We did that with the integral test. It wasn't always decreasing on the example that we did. It started increasing after the first term. I'm sorry, it wasn't always decreasing. It started decreasing after the first couple terms, and then everything's okay, right? Because a couple terms isn't going to make a difference whether your series converges or diverges when you have an infinite number of terms. Okay, so it says, make a guess about the convergence or divergence of the series and confirm your guess using the comparison test. So what makes these problems a little challenging for students is that you only have one series. What you're supposed to do is come up with your own series and compare it to that. And so with only having one series, how do you know what you're supposed to do? Well, that's what the discussion was about at the beginning, right? So it turns out that when you have a fraction like this, you can ignore all but the largest growing terms in the numerator and all but the largest growing terms in the denominator. So the series that you should compare this to then will be k equals 1 to infinity, and there's only one term in the numerator, so we'll do that. And in the denominator, we have the k to the fourth plus k. The fastest growing term there is k to the fourth. And we get, this is what we're going to compare it to, 2 over k to the fourth. Now you should know what this series does. That 2 is just a constant. You can pull it out. No need to show this work, but I will do that. You can pull it out using your limit laws, and this becomes a summation from k equals 1 to infinity of 1 over k to the fourth. This is a p series, with p being 4, which is bigger than 1, so this converges. So since this series converges, right, what we need is for the terms of this one to be smaller, right? Now, so I need you to show that to me. And so here's how we're going to do that. We're going to start here with clearly k to the fourth plus k is bigger than k to the fourth. And so then now when I flip it, 1 over k to the fourth plus k will definitely be less, because we switched the inequality, than 1 over k to the fourth. So these terms are bigger than these terms. Oh, I'm sorry, we don't have the 2, so then we could just multiply both sides by 2. And so then we get 2 over k to the fourth plus k is still less than 2 over k to the fourth. So then 2 over the summation of 2 over k to the fourth converges. We've already talked about that. Therefore, the smaller one, right, because those terms are smaller, 2 over k to the fourth plus k converges. That's the basic comparison test. For our next series, we have a k plus 1 over k squared minus k. So again, you can ignore the 1 in the numerator and the minus k in the denominator, and that will leave you with k over k squared, which simplifies to 1 over k. Now, 1 over k, you should know what that does. That's the harmonic series that diverges. And so we're assuming then, it says make a guess about the convergence. So we're assuming that this is going to diverge, since 1 over k diverges. So we've made the guess that we're going to compare this with k over k squared, which then simplifies to 1 over k. And so then we have to go and show that the terms of this series are actually bigger than the terms of this series right here. So this gets a little challenging. The inequalities aren't obvious, but we'll start here. So this series diverges because it's the harmonic series. So we'll start right here with k squared minus k is obviously less, right? And that way then when we flip it, and then it will be bigger. And k squared minus k is obviously less than k, right? And so then, which is equal to Um, K squared minus k is obviously less than k squared plus k. And the reason why I came up with k squared plus k is because we're going to bring in this k plus 1 here in a little bit. And so in order to cancel that out so that I can get back to 1 over k, I decided to compare it to not k squared, but k squared plus k. So then when I flip it, 1 over k squared minus k is bigger than 1 over k squared plus k. And then when I multiply both sides by k plus 1, I will get the terms that the formula for the terms that I have in here. So I will get k plus 1 over k squared minus k is bigger than k plus 1. And here's why I did the k squared plus k, so that I could then factor out the k and write that as k plus 1. And now this cleans up to 1 over k. And so this works out very nicely. We've just shown that k plus 1 over k squared minus k is bigger than 1 over k. The 1 over k diverges. Therefore, the series that I was given also diverges. And so coming up with these comparisons is not very easy. There's no formula for it. It requires some time for you to get comfortable with it, so you need to practice this. You should pause the video and try and do this problem on your own. You have 1 over 5 to the k plus 2. So again, you should recognize that the plus 2 in the denominator can be ignored, and what's going to happen with the series is mostly determined by the 1 over the 5 to the k. And again, the 1 over the 5 to the k can be written as 1 over 5 to the k, which then allows you to see it as a geometric series, and the common ratio is 1/5, and so the series converges. So then if the series converges, then we need to show that the terms of this series here are smaller, and so then that one will converge as well. And so to do that, it's pretty clear that 5 to the k plus 2 is bigger than just 5 to the k. And so then when I flip them, 1 over 5 to the k plus 2 is going to be less than 1 over 5 to the k. So the terms of this series are less than the terms of this series, therefore your original series converges. So we want to use the comparison test to determine if the series converges or diverges. This test is sometimes it's very difficult to use. In the last problem, it was very easy to use. In the problem before, it took a little bit of work to get there. But this one here is also a little challenging. We're going to go through this together. Okay, so you need to be careful because your test is sometimes inconclusive. So right here, it is very clear that k squared minus 7 is less than k squared because we're subtracting 7. So when I flip it, I get 1 over k squared minus 7 is bigger than 1 over k squared. But 1 over k squared converges, but the theorem doesn't tell me anything about what a series whose terms are bigger than a convergent series does. So the test is inconclusive because your terms are bigger than a series that converges. If your terms are bigger than a series that diverges, then your series diverges. That's not what's going on here. So we're going to need to start over. So again, you need to be careful with what you're doing. You need to make sure that if you think a series converges, then you show that your terms are smaller than those of a convergent series. If you think the series diverges, then you need to show that your terms are bigger than those of a diverging series. So again, here, we're again basically ignoring the 7 on the bottom, and we have 1 over k squared. You should know that 1 over k squared is a p series with p being bigger than 1, so this thing converges. So it's not a good idea, or it doesn't help, to show that these terms are bigger than these terms, because that doesn't tell you anything. Because this one converges, you have to show that these terms are smaller. And so then we want k squared minus 7 to be bigger than some relationship with k squared. Notice that I started my series here at 3 so that my terms would always be positive. We're only doing this with positive terms. But it really doesn't matter if a first couple terms aren't positive or if a first couple terms aren't in the right comparison, because it's just a couple terms, right? If eventually it happens, that's what really matters. But notice that, so we want this to be bigger than some expression in k squared. So when I put in 3 on the left, I get 9 minus 7, I get 2, and on the right I get 9. And so then on the left I get 2, and on the right I get 9. Clearly this inequality is not true. Now, so what we can do though is we can divide this by 9. And now when I put in 2, I get 9 minus 7, which is 2, and over here I get 9 divided by 9, which is 1, and now the left really is bigger than the right. So this inequality is true. At least it's obvious that it's true for 3 when we put in 3. But if you look at this, this is k squared minus 8/9 k squared, because now if I combine the like terms, 1 minus 8/9, 9/9 minus 8/9 is 1/9, and you get this expression here. And now when you put in 3, you're taking away 8, whereas over here you were only taking away 7. And because this is just getting bigger for 4, 5, 6, 7, and so on, taking away this will be you will be taking away more than if you take away 7. So different ways of looking at that, but it's true that k squared minus 7 is bigger than k squared divided by 9. And so now if I flip this, then 1 over k squared minus 7 is less than 9 divided by k squared. Now again, this 9 is just a constant. We can factor it out. So then 9 divided by k squared converges because it's a constant times a p series. Therefore, 1 divided by k squared minus 7 converges. Again, here we want to use the comparison test to determine if the series converges or diverges. And we're working with 1 over the square root of k plus 2. Again, we can ignore the 2 and we will have 1 over the square root of k. And what that is a p series with p being a half. Because that's less than 1, we're assuming that this thing is going to diverge. Now, but the only problem is that plus 2 makes the terms smaller in direct comparison. So we're going to have to make an adjustment. And so then again, what we're going to do is we're going to use a multiple factor to make that smaller. So again, ignoring the 2, we're looking at the series 1 over the square root of k, which is just the p series 1 over k to the 1/2. And so then this diverges because your p is less than 1. And so then when your p is less than 1, you have a divergent series. But again, because it diverges, what we need is we need these terms right here to be more. So then we can start with the square root of k plus 2. We want it to be less than the square root of k. Now, obviously that's not true, because when you take the square root of a bigger number, k plus 2 is bigger than k, then you get a bigger number. But what we can do is we can put a factor inside here. So starting at 1, 1 plus 1, I'm sorry, 1 plus 2, I'm sorry, this is in the wrong spot. Okay, so I fixed that. You have the square root of k plus 2. That's clearly not less than the square root of k, right? Because you're adding 2, and over here you don't have anything. But when we put in 1, square root of 1 is 1, plus 2 is 3, and over here we just get 1. And so then 3 is obviously not less than 1 unless we multiply it by a quarter. And so then so we didn't have to use a quarter. Any scaling factor would do that, as long as what we're going to do is putting in this quarter here. So square root of 1 is 1, plus 2 is 3, and I just wanted to make it less than 3. Ooh, I did this wrong. This doesn't work. If I put in 1, 1 plus 2 is 1 plus 2 is 3. We want to make this more than 3, not less than 3. So we should multiply by 4, right? Not 1/4. So let me go ahead and get rid of this 4th. We should have used a factor of 4. Now it's true. Now when k is 1, 1 plus 2 is 3. Square root of 1 is 1 times 4 is 4, and 3 is less than 4. And again, this is the square root of k plus 3 times the square root of k. And that makes it easy to see that it doesn't just work for 1, it works for all of them. Over here, you're taking the square root of k and adding 2. Over here, you're taking the square root of k and adding 3 times the square root of k. But since my k is 1, 2, 3, 4, the smallest that this can be is 1. So over here, we're adding more than 3. And over here, we're only adding 2. So this is clearly true. So now, then 1 over the square root of k plus 2 will be bigger than 1 over 4 times the square root of k. And the 1/4 we can ignore because that's just a constant. And so this series converges. Therefore, and these terms are bigger than one that converges. Therefore, your series 1 over the square root of k plus 2 converges. Now, so the last 2 examples were made to show you how difficult this can be. So rather than a direct comparison, Theorem 9.13 allows us to use the limit comparison test. And again, we're requiring only positive terms. And if we find the limit as n goes off to infinity of a sub n divided by b sub n, and we get a finite number. So back to Theorem 9.13. 13, the limit comparison test. This is going to be easier to use because we don't have to go through all the inequality gymnastics. And basically it just says that if you take the ratio of a sub n and you divide it by b sub n and take the limit as n goes off to infinity, if that limit is finite and positive, meaning it's not zero because everything is positive here, then both series either converge or diverge. Right now, we're not going to go through a big formal proof of this, but I'd like you to think about how that works. Okay, so if we know that the limit as n goes off to infinity of a sub n over b sub n equals L, then again, what this means is that as we get further and further along the sequence, or as we put in bigger and bigger numbers for n, the ratio a sub n over b sub n gets closer and closer to L, and we can get as close as we want as long as we go out far enough, and we just keep getting closer and closer. That's what that means. So then that means that you can pick any number you want to here, and for convenience we'll pick 1. So then that implies that eventually a sub n over b sub n will be less than L plus 1, right? You can go out far enough so that your terms, so that the ratio a sub n divided by b sub n is less than L plus 1. And then if we multiply both sides by b sub n of this inequality, we get that a sub n will be less than this constant L plus 1 times b sub n. And then again, we're in the basic comparison test, except that it doesn't have to happen for all terms. It happens eventually. And so then if b sub n converges, then this constant times b sub n will converge. And so then, and a sub n is less than that, well then a sub n is going to converge. If a sub n diverges, then we could divide both sides by 1 over L plus 1. I'm sorry, by L plus 1. Then if a sub n converges, then L plus 1 will also diverge. I'm sorry, a sub n over L plus 1 will also diverge. And then b sub n is bigger than that, so then that will diverge. And so that's basically the gist of the proof of that. We're not going to get any more rigorous than that. But that's our proof. Okay, so use the limit comparison test to determine whether the series converges. Again, so to use the limit comparison test, it's still a comparison test. You still have to come up with a series, a known series to compare it to. And again, you can just ignore the all but the fastest growing term in the numerator and denominator. And so then in that case, then you should be comparing it to 1 over 9k. And then 1 over 9k you should recognize as a constant, 1/9 times the harmonic series, and so then this diverges. And so then, using the limit comparison test, we're supposed to take the limit as n goes off to infinity of a sub n divided by b sub n, and it makes absolutely no difference which one you consider to be your a sub n, which one you consider to be your b sub n. That plays no role in this. We'll go ahead and let this be our a sub n, and we'll let this be our b sub n. And so then, since we're supposed to divide this one by this one, and going over what you learned in arithmetic, this is the limit as n goes off to infinity, that to divide, we multiply by the reciprocal. So we have 1 over 9k plus 6. Ooh, I'm mixing my input variables here. It should be 1 over 9n plus 6, and then 9n over 1, right? So let me start over. Let me pause that real quick. So I'm mixing my letters here. What you call them doesn't matter, but I will call this A sub k and this B sub k instead of letting my counter be n, because here the counter is k. So the input variable doesn't matter. But again, we're going to take the limit, not as n, but as k goes off to infinity, of the a sub k divided by the b sub k. And again, makes no difference which one you use, which one is a sub k, which one is b sub k. And then we're going to take the limit as k goes off to infinity. Since we have fractions, we deal with fractions by multiplying by the reciprocal, 9k plus 6 times 9k over 1. And so then this is the limit as k goes off to infinity of 9k over 9k plus 6. And last semester, when you had a rational expression and the degrees were the same, what you would get is the leading coefficient of the numerator, 9, over the leading coefficient of the denominator, 9. And so since this is 1 and it's not 0, and it's finite, that the limit comparison test tells you that the series you were looking at diverges, because the series you compared it to diverges. So in our next problem, we're going to be doing the same thing. We want to use the limit comparison test to determine whether the series converges. And this looks kind of hairy and ugly. But again, if we were to expand all this out, I don't want to take the time to expand all this out. I don't have to. If we were to expand all this out, we would get a k squared on top from the k times the k, and we would get a k times k times k, a k cubed on the bottom. And so then what we would get, what we want to compare this to, is the summation of k squared on top over k cubed on the bottom, which is then again just the summation that cleans up now nicely, 1 over k, which diverges, and because it's the harmonic series. And so then we limit comparison test, then we're going to take the limit as k goes off to infinity of the a sub k divided by the b sub k, which is then going to be, to take this again will be my a sub k, the limit as k goes off to infinity of k times k plus 3 divided by k plus 1. I don't want to take the time to expand this. K plus 2, don't need to. K plus 5. And then you multiply by the reciprocal, so multiplying by k would give you an extra k here. And now when you're taking this limit, you look at the degrees. If I were to multiply all this out, the first term would be k cubed. On the bottom, the first term would be also k cubed. And so then what you would get is k cubed 1 over 1. So this is 1. Therefore, converges, right? Diverges. Diverges. Because the series I'm comparing it to diverges. This series diverges. Earlier we did this problem. It took us a little bit of inequality gymnastics to use the comparison test because of the -7. Made the denominators bigger even though we had a series that, I'm sorry, made the terms bigger, and that didn't help. But with the limit comparison test, we can do this a little quicker, a little bit more, with less effort. Again, so what we want to do is we want to figure out what we're going to compare it to, and we just dump the 7, and we're going to compare it to 1 over k squared. Right? Now this is a p series with p being bigger than 1, so this converges. And so then we take the limit as k goes off to infinity of the 1 over k squared minus 7 times the reciprocal, which would be just times k squared, and then this would be 1. Therefore, the series converges. Nice and easy. No need to break the brain trying to figure out the correct inequalities. There we go. And moving on to our next example. In exercises 17 through 26, use the comparison test to determine the convergence or divergence of the series. Okay. Doing this problem with the basic comparison test would be quite a challenge, but here we want to use the limit comparison test. So again, if we ignore all but the largest growing terms in the numerator and denominator, we will get 2 to the n over 5 to the n. Since they both have the same exponent of n, this can then be rewritten as the summation of 2/5 to the n. You should now see that this is a geometric series. Your common ratio is 2/5, which is less than 1, therefore converges. And so then that's what we're going to compare it to, right? So now we want to look at the limit as n goes off to infinity of the a to the n, 2 to the n plus 1, over 5 to the n plus 1, times the reciprocal, which is going to be 5 to the n, over 2 to the n. Writing it as in this form right here, 2/5 to the n, that was going to make things more difficult. So for the comparison, it's going to be better to use this fraction form right here. Then this becomes the limit as n goes off to infinity of, we get a 5 to the 2 to the n times a 5 to the n. We can rewrite that as 10 to the n because they have the same exponent. You can take out the exponent, leaving behind 2 times 5. That's one of the rules of exponents, plus 5 to the n. And then over here on the bottom, you're also going to get a 10 to the n plus a 2 to the n. Okay. Now, so in this expression right here, again, the trick that we learned for rational functions, this is not a rational function. You don't have a polynomial over a polynomial. You have the sum of two exponential functions over the sum of two exponential functions. But we can modify the trick that we learned. We take whatever's growing fastest in the denominator, which is this 10 to the n, and we multiply by 1 over 10 to the n. And same in the numerator and denominator. That's just modifying the trick that we learned for polynomials, right? And so then this will equal to, still taking the limit, as n goes off to infinity. And when we multiply, when we distribute, and we should have parentheses here because we have two terms in the numerator. And when we distribute, right, so 1 over 10 to the n times 10 to the n is going to give us a 1. And then because these both have a exponent of n, we can rewrite that as 5 over 10 to the n And then over here we'll have a 1 again, plus 2 over 10 to the n. And now notice that the only place that there's a variable is right here and right here. Both of these are exponential functions. Both of these have a base that's less than 1. And so then both of these go to 0. And so your limit is 1. And therefore, your original series converges. Since your comparison series converges, and so then your original series also converges. So in exercises 17 through 26, use the limit comparison test to determine the convergence or divergence of the series. In keeping with our trick that we've been using, where we look at the numerator separately, look at the denominator separately, and eliminate all but the fastest growing terms, what we're going to do here is we are going to distribute the 2 to the n minus 1. And so then we have n over n times 2 to the n minus 1 plus 2 to the n minus 1. This isn't a law. This is just a trick that seems to be working. So we have in the denominator, we have 2 terms. And this one is n times 2 to the n minus 1. This thing is going to seem to be growing the fastest, is going to be contributing the most. And so it seems like we should be able to ignore this. And you should notice that if we ignore this, one of the nice things that's going to happen is this n is going to go away. So we're going to compare it to the summation of n over n times 2 to the n minus 1. Because then the n's will cancel out, and we get the summation of 1 over 2 to the n minus 1. And then this one is just a geometric series which converges, right? So you should recognize that as a geometric series which converges, right? And so now then what we need to do is take the limit as n goes off to infinity of n over n plus 1 times 2 to the n minus 1, and multiply it by the reciprocal of this one, 2 to the n minus 1 over 1. The 2 to the n minus 1's go away, and then what you get is the limit as n goes off to infinity of just n over n plus 1, and this limit is 1, therefore converges. Same thing, use the limit comparison test to determine the convergence or divergence of the series. For this one, this is different than what we've seen before. We're taking the sine of 1 over n, right? We're being asked to use the limit comparison test. So we don't have a choice, but it's very difficult to see what to compare it to. When I saw this problem, what sparked in my head what to compare it to is the fact that I know that the limit as x goes to 0 of the sine of x over x, I can find that limit very simple, and that limit is 1. So if what's inside the sine is the same as what's inside the denominator, and if they're both going to 0, then the limit is 1, right? So that's what I was thinking when I saw this, right? And it turned out to work. So this is what I was thinking. So let's go and approach this problem. And so then what I decided to compare this to is just 1 over n. 1 over n diverges because it's the harmonic series. And so then we're going to take the limit as n goes off to infinity of the sine of 1 over n over 1 over n. And then again, the inside is going to 0, and it is the same. And so that result that I just recalled from last semester tells me that this limit is 1. Therefore, they both diverge. Since this one diverges, this one does the same thing by the limit comparison test. That is it. There's your homework for this section. The class notes are also uploaded. Again, just a reminder, this is an hour long. Don't try and listen to it all in one shot. Digest it a little bit at a time. Practice some homework. Go stretch a little bit. Most importantly, be safe.